Um, so, last class we discussed in rather general terms the sorts of interactions that we'll be interested in considering in quantum field theory. And as you probably know, the machinery that we'll end up developing in order to study interacting quantum field theory is known as the perturbative Feynman diagram technique. There are actually several different ways of deriving the Feynman diagram technique for studying perturbative contributions to correlation functions or to scattering processes in quantum field theory. I can think of at least 3 different ways of deriving them. For example, in the textbook in chapter 4, the approach that they use is called the canonical approach to their derivation of Feynman diagrams. Actually, last year when I taught this course, I used what's known as the Schwinger-Dyson equation, which is another way of deriving Feynman diagrams. But I think probably the most elegant and clean way of deriving the Feynman diagram technique for studying perturbative corrections in quantum field theory is by the use of path integrals. And at the end of the day, there are certain things, I think, that you can't actually really ever understand precisely without thinking about the theory in terms of path integrals. So I decided that this year when we taught the course, instead of sort of beating around the bush, we would just derive directly into the theory of path integrals and how they're used in order to study perturbative corrections in quantum field theory. So I thought I would start by just reviewing for you the theory of path integrals in quantum mechanics. This is something that you've probably more or less seen before. Okay, at least some of you have seen it before. But I thought I might as well make this course self-contained and just present the theory of path integrals in quantum mechanics. And in particular, what I'm going to do by the end of this lecture today is discuss some aspects of the theory of path integrals in quantum mechanics that you probably didn't see in your quantum mechanics course, even if you did study the theory of path integrals there. Okay. So to begin with, let's just imagine that we have some sort of quantum mechanical system with some degree of freedom, or some number of degrees of freedom qi, where I is an index that labels the different degrees of freedom. So you could have a collection of n particles labeled by an index I. Or, of course, and this is the example that we might be interested in this class, you could have 1 degree of freedom per point in space. So in that case, you might use the label x vector to label the different degrees of freedom. But for now, just to keep things general, I'll use the label q. So we don't necessarily have to be talking about a field theory with 1 degree of freedom per point in space, but we could be talking about some more general system. And the sort of thing that you might want to understand is how to compute, for example, the transition amplitude that would describe a system which starts out in some configuration qi at some initial time ti and ends up in some final configuration qf at some time tf. Okay. I see here I'm using I here. I is supposed to stand for initial. It's not supposed to be one of those indices, so maybe I could call these guys Q alpha, okay, instead of Qi. So Qi here stands for Q initial, some initial value of the degrees of freedom. Qf is the set of final values. If, for example, you were just studying the motion of a single particle, Qi would be the initial position of the particle, and Qf would be the final position of the particle. And we want to study this transition amplitude as a function, say, of T final minus T initial. So this is the basic object of interest in quantum mechanics. And the beginning of the theory of path integrals really starts with an observation of Feynman. And actually, I think this goes back before Feynman to Dirac even. What we want to do is use the fact that we can always insert a complete set of basis states at any intermediate time between Q initial and T final. So we're going to imagine inserting a complete set of basis states we could call them, say, qt, at some intermediate time, t, that's between t initial and t final. So what would happen if you did that? Well, the transition amplitude for the particle to move from a location q initial at t initial to q final at t final will be then an integral over this intermediate time of the amplitude for the particle first to go from q initial to q at time t, followed by the amplitude for the particle to go from position q at time t to its final position, qf, at time t final. So I haven't done anything here except insert an intermediate state. So, I really haven't done anything here. And now I'm just going to not do anything again, and I'm not going to do anything again many, many times. So in particular, what I'm going to do, just to sort of make the notation a little bit clearer, is I'm going to give a name to t initial and q initial. So I'll call q initial, t initial, I'll call that q1, t1. So we're going to start out at some initial time t1 at position q1. And similarly, I'll call the final time and position qn and tn. And this intermediate time, I'll call it q2, rather than just q and t. And so what I want to imagine doing is not inserting just a single intermediate basis at some time t2, but rather I want to insert some large number of basis states. So this will be an integral over q2 up to qn minus 1 of first a transition amplitude for the particle to go from q1 to q2, and then q2 to q3, q3 to q4, until finally going from qn minus 1 to qm. So if you want a picture in your mind associated with this, you should imagine thinking of a particle that starts at a position q1 at some initial time and ends at some position qn at some final time. And then we've chosen some set of intermediate times, and you're integrating over all possible trajectories that the particle could take between q1 and qn, at least in a discrete sense. So each one of these transition amplitudes here is some sort of amplitude, say, for a particle to go from q1 here to q2, and then a transition amplitude from q2 to q3, all the way up to qn. And then, as you can probably anticipate, what we want to do is then take the limit where n goes to infinity, so that the time difference between two of these times, say ti and ti plus 1, will go to 0. So the time step, which is, what is that, tn minus t1 divided by n minus 1, the total number of intervals that we break this guy up into, is going to go to 0. So in this limit, this transition amplitude should become a sum over all paths that the particle could take between an initial position q1 and some final position q2. And the important thing to keep in mind here is that we're summing over all possible paths that the particle could take, not just paths that solve the classical equations of motion. because we had to integrate over a complete set of basis states. Not just, so for example, the particle doesn't necessarily move on a straight line between Q1 and Q2 or Q2 and Q3 or anything like that. There's no imposition at this point that you have only classical solutions to the equations of motion. So including those which violate the classical equations of motion. So what does this mean a little bit more formally? Well, this means that you should be able to think of this transition amplitude as an integral over all paths, a sum over all paths. I'll use the symbol capital D of Q to denote a functional integral, which that is to say an integral over all possible functions Q of t. And the boundary conditions on this integral, so every integral needs boundary conditions if you want to get a number out of it. The boundary conditions are that this function Q of t should have fixed values at its endpoints, namely that Q at t initial and Q final should be Qi or Qf. So there are really two things that we're going to need to do in order to make this idea precise. So the first thing that we need to do is we need to understand what it means to integrate over a space of functions as opposed to just integrating over some finite dimensional space like you might have learned to do in your classes on single or multivariable calculus. And the second thing we need to do is we need to figure out exactly what it is we're trying to integrate here. Right? I told you that this took a form of an integral, but I wrote down this integrand here. It was some complicated product of a large and, at the end of the day, infinite number of terms. And so we need to understand exactly what that thing we're integrating looks like. And indeed, later on in this class, I'll derive exactly what that something is by staring at that product of terms, the product of transition amplitudes in a bit more detail. But the first thing that I want to point out is that there's in fact a very, very easy way of guessing precisely what that integrand in this sum over paths should look like. Maybe before I make that guess for you, let me pause and see if there are any questions. I mean, I'm assuming this is somewhat familiar to many of you. Have you guys have seen this before, more or less? Okay. It's a deep enough and interesting enough idea that it really is worth thinking about carefully. So there's no harm in seeing this, multiple times. Any questions before I continue? Okay. So simply the superposition principle of quantum mechanics, which is simply the principle that you can take two different possible paths and add them together, is really all that you need in order to conclude that transition amplitudes in quantum mechanics should be computed by a path integral. So it's really a very, very kind of core feature of quantum mechanics. And it's kind of remarkable that although quantum mechanics was developed in the very early part of the 20th century, it really wasn't until the 40s that the path integral formulation of quantum mechanics was even stated in anything close to a precise form. Interestingly enough, if you actually read Dirac's book on quantum mechanics, which was written in 1932 or 1933, there's some footnote where he clearly had more or less the idea of the path integral formulation of quantum mechanics. He says that a particle takes all paths and that there's a particular weight associated with each path, but he doesn't actually sort of write it down and try and, he says it as words, but he doesn't take it seriously enough. It took Feynman to take it seriously in the 1940s. Good. Okay. So let's try and just guess what the integrand of the path integral in quantum mechanics is. Well, first thing you know about this is that we know how this transition amplitude should behave in the classical limit. In particular, in the classical limit, that is to say, when h bar goes to 0, this transition amplitude should be a function only of the classical path that solves the equations of motion. In particular, the classical path that solves the Euler-Lagrange equation, which says that the variation of the action with respect to the path is equal to 0. So the question is, what sort of something could we write down which has the property that when you take the limit that h bar goes to 0, this integral depends only on the solution of the equation ds by dq is equal to 0. Now, it turns out that integrals with this property are something that are very, very well understood for finite dimensional integrals rather than path integrals. And in particular, what I want to do is remind you, well, either remind you or teach you about a particular method for approximating integrals, which works for finite dimensional integrals, and in fact can be generalized to infinite dimensional integrals of the sort that we'll be considering in this class. And this is known as the method of saddle points. Well, physicists tend to know it as the method of saddle points. Mathematicians tend to know it as the method of stationary phase. It's really one of the most important approximation techniques in the theory of integration. For some reason, it's something that's not actually ever really taught or stated clearly in math classes. So I thought I would just state it very clearly now, once and for all. So what I want to do is just consider some sort of one-dimensional integral. So let's consider the following integral. Okay, I'll call it z. And let's imagine that I'm integrating over a single variable q. Okay, this is now a one-dimensional integral, not some path integral. Q is just some one-dimensional variable. And I want to integrate the following function, e to the lambda f, where f is some sort of function. I put that e there. I could have just said I'm trying to integrate some function f. I put that e there just for the sake of making some of the future formulas that I'm going to write a little bit more clear. And I want to do this integral where this function f, it has some functional form. Well, I want this integral to converge. So f better go to minus infinity when q goes to plus or minus infinity. So let's say that we're doing that integral. And then it'll have some sort of behavior in the for finite values of q. And I could add more wiggles or something like that. So now, of course, in general, this integral may be impossible to do. But I want to perform this integral in the limit where lambda gets very large. Now, when lambda gets very large, this integral should be dominated by the maximum of the function f. And in particular, it should be dominated by the value of the function f at those points q star where the derivative of f is equal to 0. And what is this function z in the limit where lambda becomes very large? Well, you'll get a contribution from one of those maxima, which goes like e to the lambda times f evaluated at the maximum. So in general, if you have many local maxima, you'll expect that there's some approximate result for this integral, which looks like the sum over all q star, such that f prime, let's say, call it df by dq star, such that the df by dq evaluated at q star is equal to 0 of e to the lambda times the function at that point. So, for example, you would get one contribution to the integral coming from this point here. That point is a little higher than the other point, so that's the global maximum. That's the thing that's really going to dominate the integral. But you would also expect some other contribution from that local but not global maximum right there. Now, this is just an approximation. It turns out that there is a series of subleading approximations, subleading corrections to this approximation. So the method for determining the subleading corrections to the saddle point approximation is essentially the method of Feynman diagrams. Okay, it's the method of Feynman diagrams applied to a simple one-dimensional integral. It's a quite straightforward exercise to work out the first correction. So that's something that I've written here involving the second derivative of the function. That's a correction that you'll work out on the problem set that I just handed out. In the language of Feynman diagrams, that's something that you would call a one-loop correction to this integral, because when you organize this in terms of Feynman diagrams, it'll come from diagrams that contain a single closed loop. And then there are other corrections here that would be referred to as higher loop corrections to the saddle point approximation. But at the present time, I just want to focus on this term right here, which, well, we would usually call that the tree-level contribution or the classical contribution to this integral in the language of Feynman diagrams. So what I want you to do is I want you to compare what we know about the path integral to what we've just learned about the method of saddle points. So for a path integral, we're integrating something dq, and it has to have the property that when a certain parameter h bar becomes very small, the integral is dominated by those values of q for which ds by dq is equal to 0. And you should compare that to what we just learned about the method of saddle points, where an integral dq of something, of e to the something times f, is going to be dominated only by those points where df by dq is equal to 0. So you see, if you squint a little bit and you allow yourself to replace the one-dimensional integral dq by a integral over all paths, q of t, and you replace this simple one-dimensional derivative df by dq here by the functional derivative, the variation of s with respect to the path q, then this method of saddle points tells you exactly what this function, this something, should be. In particular, the thing that is the integrand of the Feynman path integral should be a function of the action. And remember, the action has dimensions of energy times time. So the dimensionless thing that you can write down is 1 over h bar times the action, which has the property that as h bar goes to 0, you only include paths where ds by dq is equal to 0 for one of those paths. So the natural guess that we would make, and this is a guess that turns out to be correct, is that you should integrate over all paths, q of t, of the exponential of 1 over h bar times the action of that classical path. At this point, this is really a guess, an inspired guess, but it's something that I'll check for you in just a second. I mean, I should emphasize a couple points here. So I've included a factor of I here for reasons that, will become clear shortly. At this point, I can't justify that to you. But it's really a sort of remarkable statement, because in classical physics, the action is something that really has no meaning away from solutions of the classical equations of motion. The value of the action for paths that are not solutions to the classical equations of motion has no meaning in classical physics. It's only in quantum mechanics that that's a number that has some sort of meaning. And that's really because when you think about paths that particles take in quantum mechanics, they really travel on all possible paths through configuration space, not just those that solve the equations of motion. One other comment I'll make is that I'm being a little cavalier about how I generalize from a one-dimensional integral to a functional integral and a one-dimensional derivative to a functional derivative. For example, it may not be apparent to you that, in fact, the expression, ds by dq that I have written here is really the same thing as an ordinary derivative. In fact, it turns out that it is precisely the generalization of the finite dimensional derivative, that is to say the gradient, to an infinite number of points. In particular, you could certainly imagine taking our path integral and discretizing it. So rather than talking about paths q of t, you could talk about a point q at t1, q at t2, q at t3, and so on and so forth, where you have a large but finite number of points. That would make this an integral over a finite number of variables. And then, indeed, the variational derivative, ds by dq, is precisely the partial derivative. It's precisely the gradient grad s, okay, ds by dqi. That's, I think, probably morally clear. In all technical details, it might not be completely clear. That's okay, because you'll work it out explicitly on the problem set. And you'll see exactly why it is that in the limit we have a large number of points. This variational derivative is nothing more, nothing less than the usual partial derivative of multivariable calculus. That's something that is usually, you've seen variational calculus before whenever you learned about Lagrangians and stuff like that. But it probably was not made clear to you that the symbol that we write down here, delta s by delta q, is nothing more, nothing less than the good old-fashioned partial derivative, the gradient. Nothing fancy happening here. As usual, you can if you discretize the system, all of the sort of fancy mucking around with variational derivatives and infinite dimensional integrals becomes much, much clearer. Good. Any questions on this? So let's just, before we continue, let's just check that this is correct. So in particular, let's just try and compute this guy directly. So let's compute the amplitude for a particle to go from q1 at t1 to qn at tn. And let's just do this computation in the way that we sort of described earlier, where we imagine introducing a bunch of intermediate times, t2 up to tn minus 1, and you integrate over the possible positions that the particle could have at these intermediate times. So you want to integrate dq2 up to dqn of first the amplitude that the particle can move from a position q1 to q2, and then q2 to q3, all the way up to the amplitude for the particle to move from qn minus 1 up to qn. And now, What is the amplitude for a particle in some small interval of time, delta t, to move from a position q1 to q2? Well, we just need to use the time evolution operator in quantum mechanics, which is e to the I ht. And let's just consider the case, just to make life simple, where we have a particle moving in some potential, so that h is p squared plus v. So this is a simple example just to make our life easy in this computation. Everything that I'll say will go through in sort of a reasonably straightforward way for more complicated dynamical systems. So let's just consider the case where you have a particle moving in some potential. Then you can go ahead and study this infinitesimal time evolution operator. So what is that? So that's e to the minus I 1/2 p squared plus v of q times delta t. And let's just expand this guy out to leading order in delta t. So you'll get something that looks like e to the minus I 1/2 p squared times e to the minus I v of q times delta t. Sorry, times delta t here. And then you'll get subleading terms that are of order delta t squared. So what I'm using here is a famous formula known as the Campbell-Baker-Hausdorff formula, which says that e to the sum of two operators is e to the first operator times e to the second operator times something that involves the commutator of those operators. In the present case, I'm only working at leading order in delta t because I'm going to end up taking the limit where delta t is small. So I'm just going to ignore that commutator and all of the other higher order terms in this expansion. Okay, so I haven't really done anything yet. In order to make this a little bit more clear, let's just study this transition amplitude in a little bit more detail using this formula. So what I want to do, well, I want to do nothing again in a very clever way. I want to insert a complete basis of eigenstates, so a complete set of states. But I'm going to insert a complete set of states in momentum space rather than position space. And I'm going to insert it right here between those two terms, between the p term and the v of q term. So I have an a qn, e to the minus I delta t, pn minus 1, sorry, I should say call that p squared over 2 times pn minus 1. And then you have pn minus 1 times e to the minus I v of q. Sorry, and there's delta t's everywhere that I left out. Delta t times qn minus 1. And now I can use the fact that pn minus 1 here is a momentum eigenstate, and that qn minus 1 here is a position eigenstate, to replace those operators p squared over 2 and v over q by just functions of pn minus 1 and qn minus 1. So in particular, that's now the integral dp n minus 1 of the exponential of minus I delta t times pn minus 1 squared over 2 plus v of qn minus 1. And then you have the overlaps between qn and pn minus 1 and pn minus 1 and qn minus 1, What are those overlaps? Well, those are just the wave functions of momentum eigenstates in position space. So those are e to the I Pn minus 1 times Qn minus Qn minus 1. Okay. Now, hopefully this expression here is a little bit familiar to you. What is that? That's just the Hamiltonian evaluated at a momentum Pn minus 1 and a position Qn minus 1. So if we go ahead and put this all together, what we see is that this transition amplitude well, you get a bunch of integrals dq along with a bunch of integrals dp. So you need to do this trick where we introduce a complete set of momentum eigenstates. We do that n minus 1 times. And then you get, for each time, so you have a product from I goes from 2 up to n minus 1 of e to the minus I h of pi qi times delta t plus I times Pn minus 1 Qn minus Qn minus 1. Okay. Or, if we wanted to write this out in a slightly different way, it's an integral dq2 up to dqn minus 1, dp2 up to dpn minus 1. So you have a product of a bunch of exponentials, which is the exponential of the sum, right? Product of two exponentials is the exponential of the sum of the two terms. And so that's a sum over I going from 2 up to n minus 1 of, let's write it this way. So let's pull out a factor of I. Let's also pull out a factor of delta t. So let's write that as Pn, sorry, I didn't mean Pn minus 1 here. That's supposed to be an I. Sorry about that. So that's Pi, yeah, let me just rewrite that. Pi times Qi plus 1 minus Qi. So you get a Qpi times Qi minus plus 1 minus Qi. And I'm going to pull out an overall factor of delta t. So I'll just divide by delta t there and subtract off h of Pi Qi. And we're multiplying by delta t. Everyone with me so far? Any questions? Yes?
I'm not sure I understand how you get rid of the bracket you made the one.
Which bracket? You mean, yeah, which,
The one where you have the exponential in between the bracket with the Qn and the Pn minus 1.
yes. So I'm using, so remember the overlap between P and Q is e to the I PQ. Right? That's the statement that the wave function of a momentum eigenstate in position space is e to the IPX. So that's where those brackets went. Is that okay?
Yeah.
Good. Good. Any other questions on this? Okay. Now a miracle occurs, right? Now what we do is we take the limit where n goes to infinity, delta t goes to 0. And what is this expression? Well, we're integrating over all paths q, but we're also integrating over all possible p's as well. So what we have here is not an integral over all paths that the particle could take through configuration space or position space, but an integral over all paths through phase space, right? The space of all q's and p's. And what is the thing that you're integrating? Well, you get a factor of I. And qi plus 1 minus qi over delta t, that's just a fancy name for q dot, right? And the sum over I becomes an integral dt. So you have an integral dt of p times q dot minus h of p and q. The sum over I becomes an integral. The qi plus 1 minus qi becomes a q dot. And then we have that h of p and q. Any questions on that? And this is really our desired answer, but we've expressed this answer as a path integral over phase space. Really, there are two different path integral formulations of quantum mechanics. You can either think of the particle taking all possible paths through configuration space, or all possible paths through phase space. They're really the same. They're really equivalent, as we'll see in just a second. But before I discuss that, let me pause and see if there are any questions on this.
Is there any H bar that we're supposed to get?
Are there H bars? There are H bars, of course. I mean, there's supposed to be a 1 over H bar here by dimensional analysis. I have a habit of setting H bar equals to 1, as we are wont to do in this class. This quantity that I'm integrating, it's an integral dt of H, so there's units of energy times time. So there has to be a 1 over H bar there. Exercise, find the H bar. Right. Oh, I see it. Does anyone see it? Okay, yeah. Because the actual time evolution operator is e to the IHT over H bar. Okay. There's secretly a 1 over H bar here. Good. Right. But we're adults and we can all find our own factors of H bar. That's the definition of being an adult. Any questions? Good. Okay. Yes?
So do you have a quick concept? If our Hamiltonian was like a general function of P, general function of Q,
Yeah.
then
This argument gets a little more complicated, right? Because I used the fact that it was a function of P plus a function of Q.
yeah, but the P function was P squared over 2.
Yeah.
But if it was like general,
If you had a general function of P plus a general function of Q, this argument goes through in a completely straightforward way. The way life gets complicated if you have a function of P times a function of Q. A particle in a magnetic field, for example, has a function of is P times Z or Y or whatever it is. The argument there is a little bit more complicated, actually, but it does all go through. Good question. So we can actually rewrite this as an integral over configuration space if we just note that the integral over momenta is a Gaussian integral. Why is that? Well, H was quadratic in P, okay? So it's just some Gaussian integral, and if there's one thing I know how to do, it's a Gaussian integral. In fact, it might be the only thing I know how to do. In particular, let's just imagine that instead of, taking the delta t goes to infinity limit to write this as an integral over phase space, we just tried to do one of those integrals dp that's appearing here. What would that integral look like? Well, it would be an integral dpi of e to the I times pi squared, and I guess there was a minus sign because in that Hamiltonian, minus pi squared over 2, and then you had that linear term, which was pi times qi plus 1 minus qi over delta t. Times delta t, right? So this was the quantity that we identified as qi dot. So what is that? That's the integral of pi squared plus pi delta t times q dot. You do that, you can just do that Gaussian integral. The easiest way to do it is just to complete the squares. Right? So to complete the squares, you would just shift. Is there delta t somewhere? You would just, you would just complete the squares to shift pi to pi plus qi dot times delta t. And you would get e to the qi dot squared over 2. Is there a delta t there? Oh, there was a delta t here as well. Okay, good. Right. So that the delta t's will all factor out, right? So you're integrating e to the I delta t times pi squared plus pi times qi dot. And that's a Gaussian integral. You do that Gaussian integral by completing the squares, and the answer is qi dot squared. And there's a factor of I here. I think, if I did that correctly. Good. So what does that mean? That means when you integrate out that dp stuff, this term here will turn into a q dot squared. So what have we done here? Well, we've just used the fact that pq dot minus h is the Lagrangian, right? And that p dot squared has become the usual kinetic term, q dot squared. So this transition amplitude is just an integral over all paths through configuration space of e to the I over h bar times the integral dt of the Lagrangian. So this is a derivation. Okay, it's a slightly imprecise derivation of the fact that this something that appears as the integrand in a path integral is just the exponential of the action. I say that this is a little bit imprecise because I've been cavalier about taking limits and all of that stuff, and I haven't tried to define precisely what I mean by an integral over a space of functions. And indeed, one of the first comments that I would like to make is that, in general, an integral over a space of functions is not mathematically a completely well-defined object. You know, if you want to define an integral in mathematical terms, you need to start with a measure, and you need to define it as some limit of some series. And in general, it's something that is, complicated to define. And indeed, for the path integrals that we're studying in this class, it's not something that in general is a well-defined mathematical object, except in certain special cases. For example, for the simple harmonic oscillator, the integral is a Gaussian, okay? And Gaussian integrals are easy to do, and one can define the path integral precisely. For a general functional integral, mathematically we really don't know how to define it precisely. And so what we mean when we write down a functional integral of this sort is we mean something that is defined using the method of saddle points. So it's defined to be a classical contribution plus a series of perturbative corrections around that, which in practice could be computed using the method of Feynman diagrams. But this path integral computation is very useful because it often makes manifest many sorts of concepts. For example, it makes manifest ideas involving interference, involving symmetries. So, for example, the role of conserved quantities and symmetries in quantum field theory is very easy to understand from the path integral formulation. And it can be a little tricky to understand in other formulations of quantum field theory. And of course, for our interest, it's quite useful in perturbation theory. One final comment that I'll make is that path integrals in quantum mechanics often provide you a nice intuitive way of thinking about quantum mechanics. You know, it makes the notion of particles of interference quite clear. You know, if you think about the double slit experiment, how can a particle interfere with itself if it's just one particle? Well, the reason it can interfere with itself is that it's not going through either one of the slits in the double slit experiment. It's going through both of them. And the path integral formulation makes this absolutely clear. That it is literally the case that the amplitude involves the sum of those two different paths with a phase factor, and depending on what that phase factor is, you could have constructive or destructive interference. But although the path integral is conceptually useful, calculationally it tends to be not a very useful tool. And it turns out that in quantum mechanics, there is really nothing that you can understand with path integrals that you couldn't also understand in the traditional Hamiltonian formulation of quantum mechanics. So path integrals are really not necessary in quantum mechanics, in the sense that you don't really need them to solve any problem, at least any problem that I know about. But they're really necessary in quantum field theory. In particular, it turns out that if you study gauge fields in quantum field theory, in order to precisely understand how gauge symmetry is preserved in quantum field theory, it's necessary to really think about this path integral formulation. In fact, it was really only in the 1970s that this was understood. Nobody really knew how to deal with gauge fields, with even electromagnetic fields in quantum field theory precisely. You know, Feynman came up with a set of rules that worked, but it was a very confusing subject. And for non-abelian gauge theories of the type that appear in the standard model, people really didn't know what to do. And it was really only when Fadeev and Popov in the 1970s realized that the path integral formulation of quantum field theory made all of this stuff clear, that people realized how important the path integral formulation was. You know, before the 1970s, nobody really talked about path integrals in quantum mechanics. And it was really only after the advent of quantum Yang-Mills theory and the discussion of Fadeev and Popov that it really became clear just how necessary and important the path integral formulation was. So I'm going to continue now with the computation of some other quantities using path integrals. But before I do so, let me pause and see if there are any questions. Okay. I mean, how many of you in a class in quantum mechanics, for example, have actually done a calculation involving path integrals? There's really only a few path integrals that one can compute precisely. Like you can compute the transition amplitudes for a harmonic oscillator, and that's about the extent of what one can do. I mean, as far as a precise path integral. Of course, you can use path integrals to do approximations, which is what we'll do in this class. We'll get a lot of practice with it. But you know, the subject of path integrals is both sort of beautiful and disappointing, because it's a beautiful formalism that is nearly useless until you need to do it, until you need to do quantum field theory. And then it is literally the case there are no other ways of understanding certain things in quantum field theory. And even in regular quantum mechanics, understanding something like the Aharonov-Bohm effect is quite confusing in the Hamiltonian formulation, but it's a one-line thing in the path integral formulation. Not quite confusing, but it's more confusing than in the path integral formulation. So there's some things for which path integrals are useful, but really only in field theory is it necessary. So far we've discussed the computation of transition amplitudes in quantum mechanics. But of course, what we're really interested in understanding are expectation values. These are the observables in quantum mechanics. So let's ask then how we would use our machinery of path integrals to compute something like the expectation value of the position operator q in using a path integral. So here q of t is just the operator whose eigenvalues are little q of t. So here q, capital Q, is the operator that measures little q. And we want to measure little q at time t. So how do we do this? Well, again, one way to think about this is just we want to do nothing in the most clever way possible. So I'm going to introduce a complete set of basis states where I'm going to introduce a set of basis position eigenstates at time t. And I'm going to integrate over all possible values that they could take. And what do you have? Well, you have an integral dq of the amplitude first for the particle to go from t1 from position q1 at time t1 to position q at time t times the amplitude for the particle to go from position q at time t to position qn at time tn. And I'm measuring the value of q at times t, so I get another factor of q of t out front. So I haven't done anything here except insert a complete set of position eigenstates. And because I'm measuring that position, I have an insertion of q of t here. Well, we already know what the path integral formulation of this guy is, and we know what the path integral formulation of that guy is. The first one says that I need to integrate over all paths from q1 and t, all paths between t1 and t. And the second one says I need to integrate over all paths from t to tn. So overall, I get an integral over all paths with the boundary condition that q at time t1 is q1 and q at time t2 is q2. We have our old friend, the action of the path q. I'll forget our factors of h bar because we're going to use units where h bar equals 1. And we just now have an insertion of q at times t. So you see that if you want to compute an expectation value using path integrals, it's the simplest thing in the world. And it's worth emphasizing here that if you want to compute the expectation value of an operator, then all you need to do is figure out what the classical function on phase space was, or classical function on configuration space was that it came from. Okay. This q here is an operator. This q here is just a number, right? It's not an operator. It's the eigenvalue of that operator, but it's just a number. So the lovely thing about the path integral formulation of quantum mechanics is that you really don't need to think about operators. Right? You integrate over a space of functions, and then you insert in the integrand the value of the function at a particular time if you want to compute the expectation value of, say, the position of the particle at that time. Is that clear? I mean, this is an incredibly important point. Yeah, so there's a reason why I called that integral z up above, because not in this class, but pretty soon, we'll give a name to this thing. It will be the partition function. In fact, under certain circumstances, it is precisely the partition function of statistical mechanics. So indeed, as you've already anticipated, one of the things that a partition function does for a living is that you take derivatives of it and you get expectation values. The derivative of the partition function with respect to temperature is the expectation value of the energy. So the precise relationship between these path integrals and the partition function of statistical mechanics is something that we will discuss in this class, but not right now. But that's an important point. Good. Okay. Great. Well, what happens if we want to compute, say, some sort of not one-point function, but two-point function? So let's say that you want to compute, say, a two-point function between an operator at time t and another operator at time t prime. So you would naturally expect that the way you would do that in the path integral formulation is you would just insert the value of q at t and the value of q of t prime in your path integral. But now, if you think about that for a second, there's something very weird that's going on here. Because when you talk about expectation values of operators, operators don't commute with one another. And so the time ordering is important. You'll get a different answer whether you have q at t times q at t prime versus q at t prime times q at t. In general, in quantum mechanics and in field theory, operators don't commute, so you'll get two different answers for these things. But when we do an integral like this, q of t and q of t prime are numbers, and they commute with one another. So what's being computed here when I try and study a path integral integrand like this? Well, the easiest way to think about this is to just imagine breaking up this path integral now into three pieces rather than two pieces. You break it up into an integral from t1 up to either t to t prime, and then t prime up to n. And that's something that makes sense if t happens before t prime. So that, for example, if t happens before t prime, you'll get the expectation value of q first of q of t prime and then q of t. However, if t happens after t prime, you need to break up this path integral into three parts in the opposite order. And so you get the opposite ordering of these expectation values. In particular, what you see here is that the thing that the path integral computes are time-ordered expectation values. In these expressions here, the earlier times always appear on the right. And hopefully you remember in our discussion of Green's functions, I, in both the scalar and vector field case, was particularly careful to define a kind of two-point function called the Feynman two-point function, which was a time-ordered product. And the reason why I did that is that it's precisely that object that's computed for you by a path integral. So, in general, the thing that you need to remember is that a path integral where you have, say, many observables, q1 up to qn, we hear that subscript tells you that you have different observables that happen at different times. We call them t1 up to tn. So this path integral computes the expectation value of the time-ordered product of these guys. where the earlier times occur on the right side and the later times on the left. That's how you remember it. Later and left both begin with L, so that's how you remember how time ordering works. Later on the left. Good. Any questions on that? You know, time ordering also appears in other contexts. I don't know if you've seen time-ordered exponentials for Hamiltonians with time dependence. For example, if you try and write down unitary time evolution operators for Hamiltonians that have explicit time dependence, such as in time-dependent perturbation theory, time ordering of this sort also appears. And if you think about it, it really appears for almost exactly the same reason. That's something that would take us a little bit far afield, but if you ever see, for example, Dyson series and the formal discussion of time-dependent perturbation theory, then you will also get time orderings like this appearing. In fact, the Dyson series is some sort of, mutilated version of the Feynman diagram series. Maybe not a mutilated version; it's a perfect version. Okay. So I want to end with one topic that I think sometimes is a little bit confusing. So it's something we're going to have to return to. But I want to end with the following. Okay. So far, we've considered computations of expectation values in position eigenstates. And of course, in general, we're not interested necessarily in position eigenstates. We're interested in other sorts of states, such as the ground state. And what we want to do is think of a more general state, say psi, and you want to think about it as a superposition of position eigenstates. So there, again, all I've done is write one in a very fancy way. And so, for example, what we want to do, if we wanted to compute, say, expectation values in a state psi, for example, the vacuum state, what would we do? Well, let's say that we wanted to compute, if we were computing, say, the Feynman two-point function, some correlation function of a bunch of operators in the vacuum state. Well, how would we do this? Well, here, I guess I should have called these capital Q's up above, because I was using capital Q's to refer to operators. Well, what would we do? Well, we would need to first think about writing the ground state in terms of a sum of position eigenstates, and then you would need to do an integral of the sort that I've written here to rewrite the ground state expectation value in terms of a sum of position state expectation values. So, for example, if one thing you might want to do is take your initial state to be in the far past, so that it's before, say, any of the times here at which you're inserting operators, and your final state to be in the far future. So let's call the initial and final states t prime and t. Then you would get an integral dq prime, and you would have the ground state wave function at times t, and a ground state wave function at time t prime. And if you think about it, one of them has to be complex conjugated, because the transition amplitude was an amplitude between a bra and a ket. So you would have to complex conjugate, or take the Hermitian conjugate of that expression. And then you would have your path integral over all paths weighted by e to the is. And the boundary conditions on your path would say that q at time t initial is equal to, I guess I called it q here, and q at time t final is equal to q prime. So my notation there was not great. Maybe I should call this t initial and t final, and call these q initial and q final. But hopefully what I'm doing is clear here. So all of this sounds a bit cumbersome. You know, we would have to compute the ground state wave function and then insert it at some initial time and some final time. That sounds like a real pain. So it turns out that there's a very nice trick which allows us to completely circumvent this procedure, and in fact allows us to not ever have to compute the ground state wave function explicitly. And okay, this trick is a little subtle, so I want you to pay attention carefully. I have nothing up my sleeves. But what I want you to imagine doing is I want you to imagine taking some state, say the position eigenstate at time t. And I want you to imagine expanding this in terms of energy eigenstates. So what is this if you expand it in terms of energy eigenstates? So let's label my energy eigenstates with some label that I'll call n. And then what you get is a overlap of n with your state q times your state n. So I'm just expanding in a basis of energy eigenstates. And if you computed this overlap, say, at time t is equal to 0, you would need to include the phase factor here that tells us how one of these energy eigenstates evolves in time. So you would have to multiply times that usual phase factor that tells us how energy eigenstates evolve in time. Okay. So now I want to do a little trick. What I want to do is I want to imagine doing a change of variables where you take time and you make it just a little bit complex. You add a small imaginary part that I'll take to be proportional to I epsilon. And then imagine going to very early or very late times. So I suppose here I want to go to very early times. So if you go to very early times, then what does this expression become? Well, the e to the IENT, so e to the IENT becomes e to the I 1 minus I epsilon t times En. And when t goes to minus infinity, this thing will be, the different terms in the sum over n will pick up factors that are exponentially large, that go like e to the I epsilon times the energy. And so once we do this, this procedure of giving t a very small imaginary part will project out all but the vacuum state. In particular, the thing that will dominate the sum over n, and it will dominate it by an exponential amount at late times, is the state with the smallest energy. So what you'll get is the overlap between the ground state and the state with position q at time t equals 0 times the ground state. So this analytic continuation procedure picks out the ground state. In particular, here we were studying the ground state for some ket, q, and it picked out the ground state at t went to minus infinity. But, sorry, I shouldn't say projects out. It projects onto the ground state. And it projects onto the, if we were imagine doing this for bra vectors instead of kets, you would get an e to the plus I, or minus iet instead of plus iet. So for a bra instead of a ket, it would project onto the ground state at t goes to plus infinity. Well, that's great, because we wanted to set the bra to be the ground state of the far. If you wanted to compute a vacuum to vacuum, an expectation value in the vacuum, you would want to be in the ground state for the ket at past infinity, and the ground state for the bra at future infinity. So that means that if you want to compute the vacuum expectation value, where you just demand that you're in the ground state in the far past and the far future, this is just given by your usual path integral. So an integral over all paths of the usual object, so e to the is. So let's call this e to the is, with our insertions of these operators, I guess I call them little q's, but now the only difference is that we make this little rotation. So S is now the integral over, let's call it dt tilde of L, where t tilde is 1 minus I epsilon times t. So all of this might appear a little bit formal at first. Okay? I don't want, if this appears a little strange to you, I don't want you to worry about it too much at this point. This procedure that we're doing here, we're adding a little small imaginary part t proportional to epsilon and using that to project onto the ground state, in fact, is very closely related to something that we've already done in this class. So if you remember when we discussed the various different propagators that we could construct, we had this clever contour prescription that allowed us to choose different poles in the contour over P0. And if we took the propagator to be 1 over p squared plus n squared plus I epsilon, that picked out the Feynman propagator. It turned out that that epsilon in that prescription is the same as this epsilon in this prescription right here. That's something that's, I think, probably not entirely obvious. But for the time being, I just want you to note this as a clever little trick that one can do, which allows you to compute vacuum correlation functions really without ever computing the ground state wave function, which is sort of nice because the ground state wave function in quantum field theory is, in general, a very difficult thing to compute. For a free quantum field theory, it's not so bad. It's basically a Gaussian, just like the ground. A free quantum field theory is a bunch of harmonic oscillators. The ground state wave function of a harmonic oscillator is a Gaussian. So the ground state wave function in a free quantum field theory is basically a bunch of Gaussians. But in an interacting quantum field theory, computing the ground state wave function is basically an impossible task. it's as difficult or more, take your favorite random Hamiltonian. Computing the ground state wave function is, in general, an impossible task. And it's equally impossible here. But fortunately, if all one is interested in doing is calculating vacuum expectation values, then it's something that you usually don't need to do. Good. Maybe I'll make one more comment, just sort of to introduce you to some language. So sometimes we take this analytic continuation procedure to its natural logical conclusion. And in particular, you can take t tilde to be I times t. And so you just make time purely imaginary instead of real. So this is known as the Euclidean continuation. Of quantum field theory. It's an incredibly useful thing to do under many circumstances. We're not going to dwell too much on it in this class because it's useful for all sorts of reasons that are sort of subtle that I don't want to get into quite yet. But it is something that you may run into. And it's probably worth understanding why it is this is called the Euclidean continuation. The reason why it's called the Euclidean continuation is that if you remember this invariant interval in special relativity, the quantity that plays the role of distance in special relativity, if you make this change of coordinates where t is equal to I times t tilde, then how does this invariant interval look like? Well, it looks like dt tilde squared plus dx squared. And dt tilde squared plus dx squared, well, that is the invariant line interval, i.e. the distance, in some d-dimensional Euclidean space. In other words, the invariant interval between 2 points, which was t squared minus x squared, becomes the usual square of the Euclidean distance as taught to us by Pythagoras, which is t squared plus x squared. It turns out that Euclidean continuations are actually most useful when studying finite temperature physics. So in statistical physics, statistical mechanics, and in finite temperature quantum field theory, this is a very useful thing to do. We're not going to study very much of that in this class. So mostly, if we do study Euclidean continuations in this class, it'll simply be as a technical trick to make some of the formulas a little bit simpler. So I apologize for going over time for a few minutes. I should probably end, but maybe before I do so, I should see if there are any questions. Good. Okay, I will see you on Tuesday.